Bless you in the comments, I just sneezed. Okay, what we're looking at here are some notes regarding entropy. And really, we're talking about the second law of thermodynamics. Now, even though this is the second law, it's really the third law, because there's that 0 with 1 in front. But this is our second law of thermodynamics, and it deals entirely with entropy, often thought as like the chaos or the disorder of a system. Something that we know is that energy or heat must flow from it flows from hot to cold. You cannot let the cold out of your house. So like in the summer, if you got the AC on and you open up a window and your parents are like, shut that window, we're not trying to cool the outdoors. You cannot cool the outdoors. It's not a thing. The outdoors is going to heat your house. Or in the wintertime, if you're heating the house, you can heat the outdoors. Because we have to have fast-moving particles interact or collide with slower-moving particles to transfer that heat energy. It is always the hot, the high average kinetic energy, the higher temperatures, striking the cold, the lower average kinetic energies or the average temperatures. And that's how we transfer that energy. So we are always transferring energy from hot to cold. Now, this is if things are left to their own devices. This is the natural order of the systems. Yes, we can like cool things down. I know refrigerators are a thing, but in order for a refrigerator to work, you have to provide power to it. You have to have compressors and all sorts of systems and chilling factors to get that to happen. You cannot just have a box and tell the box, get cold. That's not a thing. Okay? So heat flows from hots to colds until that temperature is normalized throughout them. Now, because of this natural process, it shifts things from order to disorder. And this is where that idea of like chaos comes. And what we mean by this is, think about a block of ice. A block of ice has a nice lattice structure. It's a solid. It's well organized. As I continue to give energy to it and I heat that ice up, eventually it will go through a phase change. It will melt. When it melts, it loses that nice solid structure. It becomes a liquid. The particles are allowed to move much more freely in that liquid. That is going from order to disorder. Okay? Okay. Now, the way we write this mathematically, the shift of order to disorder, is with a delta S. Delta being a change in, a final minus initial, and this S standing for entropy. Yes, I understand the idea that entropy begins with the letter E, and I just wrote the letter S, but here we are. Just another weird thing in the world of physics. So this delta S is a change in entropy. It's a change in order, a change in disorder. And it is equal to Q divided by the average temperature. Q, we know that is some heat. That's what we've been using when we did calorimetry, when we've talked about heat flow. That's Q. But specifically talking about this, we really care about Q being the heat added by a reversible process. Now, some processes aren't exactly reversible in the real world, but we're going to stick to reversible processes, things that are theoretically able to kind of exist. Now that everything turned yellow, T is just going to be one value. It's going to be an average temperature, and it's going to be in Kelvin, proper SI units. When we talk about reversible, sometimes that can get confusing for think about. What we really mean for reversible here is that we're going to find Q, some amount of heat energy, for two states. Okay? And everything that we're going to talk about will be reversible. Now, in a later video, we'll actually dive into an example of what's going on here, but one of the interesting things about this idea of a change in entropy is that, in general, the change of entropy is equal to the change in entropy of a system plus the change of entropy in the environment. And this always has to be greater than or equal to 0 for any real process. For any real process, this must be true. If we knock a plate off of a table, that plate's going to shatter into a bunch of pieces. That makes sense. We've never seen a scenario where a bunch of pieces of plate on the floor have reconfigured themselves and then put themselves back onto the table. That's not a thing. If it was a thing, please let me know. You've discovered magic. I need to know about this because we can exploit it for our own nefarious gains. In general, the entropy of the universe, and that is what this delta S is right here, must always increase. It must always increase for any real process. Even if your change in entropy in a specific system is going down, things are becoming more ordered, such as in like a refrigerator. On a global scale, that refrigerator is still pulling power from somewhere, and that power needs to be generated. So on the environmental side of things, we are still generating more entropy. The universe entropy is increasing. Okay? It always must be greater than or equal to 0. To have 0 entropy, nothing is allowed to happen. But I guess technically, nothing could happen. In which case, if everything paused for a second, our entropy wouldn't change. So with this in mind, where does this leave us? Well, it leaves us with a few weird things to talk about. The first being, when we look into engines, because that's what we've been talking about in this class, kind of like heat engines and refrigeration cycles. When we look at engines, we have to have a change in temperature to do work. That was one of the features. We had to have some hot reservoir, and we had to have some cool reservoir, and we went from hot to cold, and then we snaked out a little bit for work. That was one of the efficiency diagrams we looked at. We have to have a change in temperature to do work. Something that can happen, though, is as this entropy increases, as we heat up cold things to warmer positions or more disorderly systems, more chaos, the temperatures are getting closer. Given a long enough time, all of the molecules in existence will interact with all of the molecules in existence, which means that everything will be the same temperature. And if everything is the same temperature, you can no longer do useful work. You will just have stuff, and you can't do anything with it. This is what we refer to as the inevitable heat death of the universe. It's just over. You can't do anything anymore. Not even you, but atoms in general can't do anything because they're just all the same temperature. So nothing useful can become of that. The universe will literally just, die. It'll just stop doing anything. So that's an inevitable heat death due to this idea of entropy. Another idea that we get from entropy is since this delta S of the universe always has to be greater than or equal to 0, and we said that it can only equal 0 if we've stopped time for a second and nothing happens. This implies that since this delta S of the universe will be some positive value as long as time is ticking, this implies that this entropy is the arrow of time. It's time's arrow. It implies that time can only go in one direction. Because for time to go backwards, you would have to reorder systems. And we cannot reorder systems. Systems must always go to disorder on a universal scale. So because of this, you can't time travel. You cannot go back and relive your 6th birthday. It's not possible. And any movie that says you can, well, they're wrong. So this is time's arrow, and it's brought about by entropy. It's kind of a weird thing, okay? One of the other kind of weird questions that comes out of this, and this is kind of like a more metaphysics question, if things have to go to a state of disorder, then, well, how do we exist? We are highly ordered beings here, right? Like, as humans, you know, we've got very specific structure in order to exist. If delta S is always going up, how did we come into existence? Wouldn't this be a violation of the second law? Well, it's still not a violation of the second law. Even though on our small system, things are becoming more ordered, on the entire environmental system around us, the energy taken to form you into your position and keep you in this kind of stable state, you are causing much more environmental, being not your own body, delta S's. So you are causing much more chaos throughout this system. In order just to survive, you have to eat and consume nutrients, which are broken down and then converted into energy by your body, which then you're giving off in terms of you're actually doing work / your metabolic rate and your heat energy you're giving off. So you're constantly increasing the delta S of the universe, even though that on your individual body in that small scale, your creation, you yourself might have been a negative entropy in a more ordered state. On a global scale, things are still becoming more chaotic, and as a result, we are still able to exist and evolve as humans. So kind of a neat thing there. You know, humans themselves don't break laws of physics. We can just describe what's going on with the physics itself, okay? So that's kind of a background on this entropy. In our next video, we'll actually take a look at solving for a delta X or a delta S in these type of problems, and we'll see how to do that. But until then, this is finished. Adios, and take it easy.